Yes, hello. Can you see my screen?
Yes.
Yes.
Yes, okay, thank you. Let's begin. So today I will tell you about my paper 2B3Net combining 2D and 3D convolutional neural networks for 3D PET scans prediction. Positron emission tomography is an imaging technique that allows to visualize the metabolic activity of cells in the body. Doctors use this modality to plan the appropriate cancer treatment. There are two main methods to exploit this image modality. First one is radiomics. Radiomics are features related to a segmented region of interest that describes this region. First step is the segmentation of this region of interest. A doctor or an algorithm produces a segmentation map of the tumor. Then radiomics can be extracted. They are related to the intensity, the shape, or the texture of the tumor. Final step is the training of the machine learning model to make the appropriate prediction. However, this method has two main drawbacks. The production of the segmentation map is a time-consuming step and is subject to intra-observer variability. A PET image is really noisy, and as a result, it is difficult for two different doctors to produce the same segmentation map. The other main method to exploit the PET scan is convolutional neural network. 2D CNN perform well on natural images. However, due to their 2D nature, they can't be applied directly on 3D PET images. Therefore, a 3D CNN is the perfect fit to exploit the 3D spatial information contained in the PET scan. There are two main drawbacks to 3D CNN that are they have much more parameters than 2D networks, and there is no pre-trained 3D model available to initialize the weights of the 3D model, meaning that we have to train it from scratch. In the medical field, PET datasets are usually small. Sorry, I hear an echo. PET datasets are usually small, and it is therefore harder to train a 3D CNN, which implies an overfitting tendency. We propose a new innovative method that takes advantage of a pre-trained 2D network and combine it to a 3D network. The first part of the architecture is a 2D network. It is helpful to use a 2D network because it will ease the training of the global architecture. The combination to a 3D network enables it to exploit the 3D spatial information contained in the scan. Finally, we assembled several public datasets from the Cancer Imaging Archive to constitute a large PET dataset. Now, I will detail the different parts of our architecture. First, we split the 3D volume of a PET scan into k 2D slices. We select only k out of n slices as we need a consistent input to our architecture. The slices are cropped to also diminish the global size of the image. Second step is that we apply a 2D feature extractor on each of the image. We used a ResNet 50 to extract intermediary feature maps. We use an intermediate layer of the ResNet so that the features extracted are relevant to our case. The extracted feature maps are of size 256 by 23 by 23. Then we combine them to reassemble a 3D volume. This 3D volume then had an additional shape of an additional dimension of k. The last step is the application of a 3D CNN to make the prediction and exploit the 3D spatial information contained in the scan. This architecture has several advantages. It has less 3D convolutional layers to train from scratch than a full 3D CNN. That also implies having less parameters to train. And the 3D volume reassembled is smaller than the original PET image. That will also contribute to facilitating the training of the 3D CNN. We evaluate our architecture on two tasks. First is a correlation of spatial information. Our objective is to compare three models on their ability to correlate spatial information between slices. We compare 2B3net to its 2D alternative version where we replace the 3D convolutional layer by 2D ones and a full 3D CNN. We make the hypothesis that a single transverse slice doesn't provide patient gender information. Then the models have to rely on the correlation of these slices to make the prediction at a patient scale. Here, we can see that 2B3net achieves superior performances compared to the two other CNNs. The full 3D CNN achieves the worst performances as it had to be trained from scratch on this task. And when we compare 2B3net to its 2D alternative version, we attribute its best performances to the fact that the 3D convolutional layers can correlate the spatial information contained in the scan, while 2D ones can't perform as a good correlation. The second experiment is a prediction of clinical outcomes of the head and neck cancer. That are the prediction of, there are three outcomes that we consider: the prediction of local regional recurrences, the formation of distant metastases, and the survival of the patient. The idea is to compare our method against a radiomics approach from Martin Valliere, published in Nature Scientific Reports. We will consider two models to compare our architecture with. First one is a machine learning model based on PET radiomics. The second one takes as input PET radiomics combined with TT radiomics and clinical data. Our model only takes as input the PET scan and have no access to any metadata of the patients. This is a difficult task as all the clinical outcomes have a pronounced class imbalance, approximately 80%. Therefore, it's also harder to train a deep learning model on this task. We added one more experimental setup to this experiment. This is a pre-training of the weights of our 2B3net with the weights of the previous experiments. This serves as a basis for fine-tuning the model. Here, we can see that 2B3net achieves better performances than 2D or 3D CNNs. It also achieves better performances than radiomics models on 2 out of the 3 clinical outcomes. It only achieves inferior performances on the prediction of distant metastasis. We attribute the best performance of the radiomics model to the information contained in the CT scan. The author demonstrated that this information allows to make a significant contribution to the prediction. To conclude, we propose 2B3net, an architecture that combines a 2D pre-trained network to a 3D CNN. This combination enables direct exploitation of 3D scans, which can be PET, MRI, or CT. And this combination is a competitive alternative to traditional CNN and radiomics approaches. Thank you for your attention. And now I would like to open the floor for questions.
Thank you for the presentation. I think we have one question from Omer Kaya.
Can you read the question? I cannot see it on the chat.
I see that Omer Kaya has raised the hand. I don't know if it's by accident or there is a question behind this. So if Omer Kaya listens to us, you can write your question in the chat forum, so we can read it. So, okay, I have one question for you. The number of slices, K, how does it affect the complexity, the computational complexity of your implementation?
Well, the more you increase the number of slices you select, the more it will increase the number of parameters of the network. As the feature maps, as the recombined volume will be bigger than if you take a small number K. In our case, we took K as a 66, as it corresponds to the size of the smallest scan. The important thing in this task is to select the number corresponding to the size of the smallest scan you have in your datasets, so you can exploit all the scans that are in it. The selection of K out of n slices of the scan also contributes to a data augmentation, as the model doesn't see every slice of the scan at each training step.